of Lagrange equation. As Sripriya has already introduced you about this topic, but I'll be dealing with another application of Lagrange equation. So, for the introduction, in classical mechanics, the motion of an object is usually explained using Newton's law of motion, right? However, when dealing with a system having constraint and a complex coordinate system, the Newton method became difficult. So to simplify such problem, we are using Lagrange equation, and it was developed by a mathematician, Joseph Louis Lagrange, and it is based on the concept of energy rather than force, making it easier to analyze complex system with constraint. Here, Lagrange equation is defined as the difference between the kinetic energy and the potential energy. Mathematically, it is denoted by N is equal to T minus V, where T is the kinetic energy and V is the potential energy. So I'll be dealing with two applications, that is a body moving on an inclined plane and object moving on a sphere. So first let us move on to our first application, that is body moving on an inclined plane. So as you can see here in the picture, here the system is the mass M sliding down a frictionless plane incline with an angle alpha, and we choose x here as the distance along the surface of the incline. So to find the Lagrange method, we need to find the kinetic energy and the potential energy, right? So for the kinetic energy, as mass only moves along the x-axis, so the velocity here will be x dot. Here x dot represents the time derivative of the position. So the kinetic energy T is equal to half m x dot, and kinetic energy is equal to half mx dot square, and for the potential energy V, here the gravity acts vertically. If x is the distance along the slope, its vertical height it should be x sine alpha. So V is equal to mgh. Here h is equal to x sine alpha, so V is equal to mg x sine. So as I told you, Lagrange is defined as the distance between kinetic and potential energy. So L is equal to T minus V. Here T is equal to half mx dot square minus T is equal to mg x sine alpha. So we'll be using Euler-Lagrange equation, that is v by dt dou L by dou x dot minus dou L by dou x is equal to 0. Here dou x dot represents the velocity, and here x represents the position. So first, by using this Euler-Lagrange, first we will differentiate L with respect to x dot. So dou L by dou x dot is equal to, from this Lagrange equation, as you can see, dou x is only in the term t, not in the term t, right? So we will take only the term t here, that is half mx dot square. This 2 will come this side, so 2 will be cancelled, so it will be mx dot. Then we will take the time derivative as a result, so v by dt dou L by dou x is equal to mx is equal to mx double dot. X double dot here is the acceleration. So then we will differentiate L with respect to x, dou L by dou x. So here x is only in the term v, we will only take the term v, that is equal to r, and here we choose spherical coordinate theta, phi, and r. Here theta is the polar angle, phi is the azimuthal angle, and r is the radius. Since radius r is constant, we are going to use only two coordinate, that is theta and phi. Here the position r is equal to capital R. So the velocity here in generalized coordinate, the general velocity square is equal to v squared is equal to r dot square plus r square theta dot square plus r square sin theta phi square. Since the particle is stuck on the surface, so r dot square will be 0. So it will give us v square r square theta dot square plus sin square theta phi square. So to find the equation method, we need to find kinetic energy and kinetic energy. So for kinetic energy, T half mv square. So T is equal to half msv is equal to LC r square theta square plus sin square theta phi square. And for potential energy, assuming the gravity acts along the z-axis, that is, z is z-axis would be r cos theta. So v is equal to mg r cos. So Lagrange equation n is equal to p minus b, n is equal to half m r square into theta square plus sin square theta phi square minus v is equal to mg r. So next we need to find the equation of motion for theta and phi by using Euler-Lagrange equation. First we will find the equation of motion for theta, that is d by dt dot L by dot theta dot minus dot L theta is equal to 0. So we'll differentiate first L with respect to the velocity theta dot, that is dot L by dot theta dot is equal to. In this equation, theta dot is only in the first term of t. So we'll take only the first term of t. Here 2 with this 2 will be cancelled, so it will be mr square theta. Then we will take the technical derivative as per the latest dot L by dot theta dot into m r square r dot is equal to m r square theta dot. So next we'll take the derivative, we'll differentiate n with respect to theta, that is dot L by dot theta is equal to term will be minus, then it will be m r square theta minus m r square sin theta cos theta phi plus mg then we'll divide each equation by mr square, so we'll get theta double dot minus sin theta cos theta plus phi square minus g sin theta by r. Now we'll find the equation of motion for phi by using Lagrange equation, that is dl by d by dt dl by dot phi minus dot by we'll differentiate L with dot phi, that is dot L by dot square. So we'll take the first term of t, that will be m r square sin square theta, and with the we'll differentiate L with respect to phi, that is dot L by dot phi. Since phi is not applicable in the Lagrange equation, there is no phi in the Lagrange equation, so it will be 0. So as dot L by dot phi is equal to 0, so the term will be d by dt into m r square sin square theta phi. So this is all